2 minutes after 8, and we've already got more participants than last time, so that's pretty good.
Nice.
Yeah, I'll just get opening remarks started then. Hey everyone, thanks for coming. This is Hacker Nights. It's hosted by my company, Multiprocess. It's just me, build open source data tools like Data Station. So if you haven't seen them, feel free to go to multiprocess.io and check those out. A reminder that Zoom chats are not stored after this. So if anyone has questions or links that they want to share throughout the talk, so now there is a dedicated channel on Discord. If you go to discord.multiprocess.io, there's a Hacker Nights channel in there. Feel free to leave your questions or links or anything in there because that is persistent. Yeah, also a reminder that this is recorded and it will be available on YouTube afterward. Awesome showing. I guess let's wait like another minute or two, and then we can let Theia go first. Am I saying that right? By the way, Theia?
Yeah, I pronounced it Theia, but
Theia, gotcha. Sorry. All right, how about let's get started. Theia, you ready to go?
Yeah, let me just get my screen sharing set up. Hopefully that's showing up all right.
Yep.
All right.
Oh, sorry, one more thing. Normally, or not normally, I've been trying to get 3 speakers lined up, but there are only 2 of you tonight, so no need to rush. Yeah, go for it.
Okay, that's good, because mine might go a tiny bit over.
Sure.
I timed it a couple times, and it was in between. All right. So hi, I'm Theia, and I'm going to talk about JPEG decoding. Yeah, let's get started. So JPEG is a ubiquitous image format, and for that, like, people criticize JPEG a lot. Like, it's got a lot of weaknesses, compression artifacts, lack of transparency, etc. But JPEG is also a really popular image format. And why is that? Well, JPEG is a format optimized for human perception. So that means, unlike PNG, JPEG isn't usually lossless. It's willing to throw away detail it thinks you won't see. Well, that algorithm sometimes breaks down. When it works, it produces really nearly flawless images at a fraction of the size of other image formats. The core of the JPEG algorithm is also at work in video codecs too, so where size is even more important. So if you're interested in the inner workings of, say, H.264 or VP9, then JPEG is a great way to introduce yourself to those basic concepts, but in a simpler environment because there's no motion. So what are those basic concepts? How does this image format actually work? So in this presentation, I'm going to explore JPEG by writing a dead simple decoder. We're not going to try to support every JPEG on the internet or be fast or be particularly correct. We'll cover the segment sequence, lossless compression layers, and finally the grand finale, the lossy compression, which is the quantized discrete cosine transform, which personally I think is really cool. There will be some code in this talk, so the slides and code will be on GitHub if you'd like to peruse at a slower pace after the talk, because I don't think it's really practical to keep up with a bunch of code on screen. I've also structured this talk in the order a JPEG file is decoded and in the order that my script is ordered. So you can follow along with the slides when you decide to rewrite this in Rust. So we're going to focus on this JPEG file, which uses a very simple subset of the JPEG format. And by the end, we'll be able to decode it and see what it actually is. So we have a bit over 5,300 bytes to deal with. So how do we make sense of this byte soup? The first layer of structure in a JPEG file is the segment sequence. A segment is, well, a segment of the file that's prefixed with a hex FF byte. It's followed by another byte that represents what kind of segment it is. For example, a start of image segment or a comment segment. And then depending on the kind of the segment, there may be additional data, in which case the kind byte is followed by a 2-byte length, and then by that many bytes of data. The first 4 bytes of our file, hex FFD8, are actually the entirety of the first segment. Hex D8 is the kind byte for start of image, a segment with no data that represents the start of the file. When stat or a file manager auto detects a JPEG file, they look for the magic number hex FFD8FF, the start of image segment plus the marker byte of the next segment. And here's a segment with some more data, a comment segment. This was inserted by my image editing program, GIMP. It holds arbitrary ASCII text, which is uncompressed since it's expected to be short. And finally, here's the weird segment, start of scan. This segment holds the actual compressed image data, so the length field is only the uncompressed header prefix. So we'll need to scan through the data following this segment, looking for hex FF bytes, and if they're escaped by being followed with it by a 0 byte, then that they're just interpreted as a literal compressed FF byte. But otherwise, it's the start of a new segment, so we can break out the scan loop. So now we know enough about segments to define a data type for them. So this is just a Python data class. We'll map the kind byte to a easier to grok string. And we can write a function that will read a single segment by first parsing the marker and kind byte from the file. And then depending on all the no data segment kind bytes fall into a specific range. So if it's in that range, then we just return a segment with an empty data section. And otherwise, we parse out the length and payload. And if it's the special start of scan segment, we just keep scanning through like I described before. And then we return the segment and then the trailing byte so that we can parse the next segment after this segment. And then we use that function to call this we use that function and call it repeatedly in a loop, reading all the segments and putting them into a dictionary based on their kind string. So now that we parse the image, we can see the structure more clearly. So we have a start of image segment. We have a app specifics JFIF segment that we can ignore, the created with GIMP comment. We have 2 defined quant table segments that we'll cover with a discrete cosine transform, a start of frame segment that holds the image metadata like width and height, 4 Huffman table definitions that we'll use in a moment, the image data in the start of scan segment, and finally the end of image scan segment. So now that we've parsed the segment sequence, we can start on the lossless compression. So JPEGs store the compressed image data in a series of 8x8 subblocks, and each subblock has a layer of lossless compression on top of the lossy perceptual compression. So let's quickly go through those lossless compression techniques, starting with Huffman coding. The basic idea behind Huffman coding is that in a sequence of data, some subsequences are more common than others. So it's worth using more bits to represent uncommon sequences if we get to use less bits to represent common sequences. So in the Huffman table above, we want to represent 6 distinct values. So the naive approach, which is in the center column, would be to use 3 bits per value. So 0 would be 000, 1 would be 001, etc. However, since 0 is much more common in a JPEG subblock than 5, it makes sense to sacrifice 5, representing it with 6 bits instead of 3, so we can represent 0 with only a single bit. Notice that none of these sequences are prefixes of each other. That means you can always read a Huffman encoded bit stream bit by bit, and once the sequence you've buffered matches one that's in the table, you can immediately emit a value. So the JPEG encoder will take care of defining the table so it has these properties for us. So to implement this, we can first whip up a basic data type for the Huffman tables. So there's multiple tables embedded in a JPEG image that are specialized to different types of values and components. The kind of a table is either AC or DC, and this will switch automatically within a subblock. DC is used for the first value and AC for the rest. And the reason for that will make sense in a moment. And then the ID will be specifically requested by a certain component. So generally the luminance or like lightness of the image component will use one table, and the chrominance color components will use a different one. So that gives 4 total tables in the file, which is what we saw in ours. So there's an AC and a DC table for 2 IDs. And then to parse these tables from a defined Huffman table segment, we first parse the ID. And the upper 4 bits of the ID byte are the kind, and the lower 4 bits are the actual ID number. And then the codes are defined as simply the Huffman codes are defined as simply a count of codes for each code length between 1 and 16 inclusive. So any data bytes after the 16 bytes of code lengths are the values for those codes. So to calculate the codes from the lengths, they just increment within a certain code length. So we just keep adding 1 to a code. And then when we reach the end of however many codes are in that code length, we multiply it by 2 to add a 0, and then just keep adding 1. And then my code doesn't do any checking to like make sure, for example, that a code doesn't overflow. I just assume the best of the encoder. And then to read values out of a compressed bit stream, I just wrote a bit stream type that really inefficiently represents bits as a list of integers. And it'll incrementally read longer and longer codes from the bit stream. And it'll try to look them up into the Huffman table. and then putting the bits back and retrying with a longer code if they don't match. So the next layer of lossless compression on top of the Huffman coding is a length prefix integer encoding. So all integers in a JPEG data block aren't represented with Huffman codes because this would bloat the Huffman tables unreasonably. So rather, the bit length of the integer is Huffman encoded and then prefixed to that many bits. So furthermore, there's a signed offset. So if the first bit following the Huffman code is 1, then the integer is interpreted as positive, and otherwise it's offset by -2 to the bit length minus 1 to get a negative integer. So in this example, you see 0 is just a single 0 bit, whereas +4 is 3 bits, 1 0 0. But -4 it takes is a oops. Oh, sorry. No, I misread this. Or actually messed up this table. I just realized. Sorry, this table is a little messed up. This should be this middle column should be 3 and then 4 for the bottom row. But basically the -4 takes a little bit more bits to represent because it needs a leading 0 to mark it as negative. So the code for this is also in the bitstream type. But I don't have a method that actually both reads the Huffman prefix and then reads that many bits for an integer trailing it, because as we'll see in a second, sometimes for some components, there's data packed into the Huffman prefix as well. So we'll go over that in a moment. So now this is basically this is the part that puts it all together, where we read the 8x8 subblock for a single color component. So the first element, like I was talking about before, is called a DC, and it works differently than the other components of this subblock because it is actually encoded as an offset from the previous subblock for this color component. So we need to store the previous DC and then read in the new DC as an offset. And then also this uses a different Huffman table, as we mentioned before. And then for the other 63 AC values, we read the header as a Huffman value, and then however the upper 4 bits of that header are special, so they're used to encode basically a number of zeros to write into the block before writing the AC value. So basically, this is like a form of run length compression. We can write an arbitrary number of zeros before any AC value with just 4 bits. And also, additionally, if the header is 0, it means that the entire rest of the block is zeros. So we can just jump out of that immediately. And again, encoding that header as 0 only takes a single 0 bit. So it's really efficient if the block is almost all zeros. And then in order to read all of those subblocks, we have to just keep reading them in order from the bitstream until the bitstream is exhausted. And then, but each component, like I was talking about how you have to keep the previous DC for a block. Each component's previous DC is separate. That cost me some debugging time. I thought that they were shared. And also, for some reason, the image components are read. So the image color components have IDs like 1, 2, 3. But for some reason, they're read in the bitstream 1, 3, 2 instead of 1, 2, 3. I'm not sure why. So now we can read a subblock. So this is one of the subblocks in our image. But if we look at it, it's it doesn't really look like image data. It's got like a bunch of numbers at the front and then a ton of zeros at the end, which is really good for compression, but doesn't really look like pixels. So what's going on here? So it's time to talk about JPEG's loss decompression technique, which is the discrete cosine transform and the quantization of such. So the discrete cosine transform is a way of representing an image in terms of a set of basis functions based off of cosines. It's if you're familiar with the Fourier transform, it's a similar idea. It's called a Fourier related transform. So the image represents the 64 basis functions used for an 8x8 JPEG subblock. So they start out in the upper left as really low frequency, and then as you head towards the bottom right, they increase in detail and frequency. So an image represented by a DCT is simply an 8x8 matrix of coefficients that represent how strong each of the basis functions are in the image. So let's look at what that looks like. So here's an animation I put together of incrementally adding basis functions to construct an image. So on the left is the basis function most recently added, and on the right is the accumulated image. And sorry for the really low resolution text on the top. I kind of screwed that up. So notice how it starts out as like basically a formless blob. And then by the end, once all 64 basis functions have been accumulated into the image, it's a lossless one-to-one copy of the original. And also notice that the first basis function, which is the upper left of the 8x8 grid, is pure white. So that's this one right here. The first basis function is just pure white. And this is the DC we were talking about in the previous section. The DC coefficient sets the intensity of the entire subblock. A high DC coefficient results in a bright subblock, and vice versa for a low DC value. So that's why the DC coefficient is treated specially, since it tends to vary in a different way from the other AC coefficients. And then these names come by analogy from DC and AC current, since DC current is constant and AC current varies sinusoidally. So at this point, you might be wondering what the point of all this is. We've taken 64 bytes of image data and turned it into 64 bytes of DCT coefficients. So what's the point? And the reason for that is quantization. This is where JPEG's optimization for human perception comes in. Humans are, generally speaking, really bad at seeing high frequency data. Without, like, when you look at a photo of a person, it's hard for you to tell whether each individual hair on their head is actually in the photo, or they just kind of have like a hair colored blur on their head. So JPEG takes advantage of this. So the image above, I've extremely skillfully drawn a zigzag on top of the DCT basis functions. So it starts in the upper left at the DC basis function and snakes over to the bottom right. When an image is encoded, a quantization table is used to divide each coefficient. Since the coefficients are represented as integers, if a coefficient is smaller than the quantization factor, it will become a 0. And then the subblock is rearranged according to this zigzag pattern. So for example, this coefficient highlighted in green is the third value in the encoded subblock, not the 9th. So since the quantization factors are higher for higher frequency basis functions, and the zigzag pattern rearranges those high frequency basis functions at the end of the subblock, this leads to subblocks with a lot of trailing zeros, which is what we saw. And this is perfect for the run length encoding we talked about earlier, which can collapse all those trailing zeros into a single 0 bit. So let's implement this. So first we'll define that the zigzag indices so that we can unzigzag our subblocks. And then we can unzigzag our subblocks with NumPy's indexing magic and dequantize them with an element-wise multiplication with the quantization table for this component. And then we'll just loop through the block tuples that we defined earlier and dequantize each set of 3 blocks, one per component. And now we can inverse DCT the dequantized subblocks. We define the DCT matrix. I won't go over the math here. It's basically just a bunch of cosine functions. And then we dot the subblock with the DCT transpose and the DCT and offset it from -128 through 0 through 255. And then if this was totally unquantized, this clipping wouldn't be necessary, where we clip it from 0 to 255. But the quantization process can kind of can cause certain values to like explode outside of that range. So we just have to manually clip it. And for implementations that are written in more efficient languages where you have like sized integer representations, this actually forces decoders to use 16-bit values for this stage instead of 8 bits, which is kind of a shame. But once you clip it, then you can make it an 8-bit value. But yeah, you just have to clip it. And then finally, the last step is we need to convert from JPEG color space to RGB. And JPEG uses YCRCB, which is luminance, Y, red, CR, and blue, CB, and then green is inferred from the other components. And JPEG uses this color mode for a few reasons, but my understanding is the major one is for compression as well. JPEG images can more highly compress, have a certain mode where they more highly compress the CR and CB components than the Y component, because again, humans are less perceptive to changes in color than we are to changes in luminance. So we don't really notice when an image is lower resolution in the color, as long as the luminance is still high resolution. But most of the defaults for encoders that I looked at tended to use equal encoding for Y, CR, and CB. So this doesn't seem to be used as much. So converting between the color spaces uses some magic constants, which are defined in the JFIF companion standard. And then off screen, I wrote some code that combines these RGB blocks that we've generated into a single PIL image, but that's not that interesting, so I won't show it here. So finally, we can see the image that we've decoded. So thanks for listening to my talk. And here's a link to the code and slides, as well as a bonus animation showing the effect of adding more DCT coefficients to a larger image. So as you can see, the blocks start to get more and more defined. But then as you kind of race through the end, it doesn't really make a difference. And part of that is because this particular image is pretty low quality. But even for higher quality images, it really falls off, and that's why quantization works so well. So again, thanks so much for listening. And does anyone have any questions?
I'll ask, get started. Why were you doing this?
There's a really interesting YouTube video that I wish I had linked to that talks about, I forget what it was called. I think it was like the unreasonable efficiency of JPEG compression or something, that talked about some of these concepts around the DCT and quantization and stuff like that, and had some interesting visualizations. And I was like, oh, that's really cool. So I started writing this decoder, and then after I finished, I was like, oh, I could show this off, and maybe people would find it interesting. But I didn't have like a practical reason for approaching it, and it's not a very high quality decoder, so I don't think anyone would actually want to use it.
No, that's awesome. I thought it must have been for like work or something, because looking through all of the complexity here, I'm like, if I were doing my first image decoder, I'd want to start out with the dumbest format possible, because this just sounds super complex.
That leads into my question.
Oh, sorry.
I said, so if this is and this is amazing, and obviously JPEG has lasted a good long while, have you done one for WebP yet? And if so, how much harder is it?
I'm not sure. I haven't actually looked into the WebP format at all. My understanding of WebP is that it's, I want to say, related to VP9, and it's like uses the same like frame encoding as VP9. I think. Don't quote me on that. But if I'm correct in that, and I think that VP9 is also a DCT based codec, so I think a lot of I think the details would be different, but I think the core would probably be similar, where it has like a DCT encoding that's then losslessly compressed and then packed into some sort of container format. But I don't know the details. I would if someone wanted to write a WebP decoder in the same vein and present it, I'd love to see that, because it'd be really interesting to see how it's different from JPEG after 20 years of development.
And when you are working on this, do you write unit tests to help you out with all the intermediate parts?
In retrospect, I spent a lot of time fighting small bugs in my implementation, and I probably should have had more tests. I just had once I finally got the whole thing working all the way through, I was able to write out like a PNG image and then do a byte for byte comparison with that PNG image as like an integration test, basically, to make sure that like some refactor or something hadn't broken things. On the way through, I did a lot of comparison with, there's I think it's called Rust image. It is a good Rust, like general purpose image decoder, and they have a JPEG implementation, and I write a lot of Rust at work, so it was pretty easy for me to go in and just add like logging to various parts of that and be like, why is my DCT different? But I ended up actually fighting just a lot of things that I think would have been hard to unit test for, because there's, for example, like misunderstanding an algorithm that was described in a book or something like that. And so if I'd written a unit test based on like understanding, then the unit test would have been wrong. So, but I tend to be more of a code first than write test after person, rather than like a write test up front and then code to get the test working. So that's just more of a matter of personal preference, I think.
Any other questions?
Yeah, basically the hard thing is to find all the specifications, right?
Yeah, it was JPEG is specifically a standard also that has a ton of extensions, and the standard itself underspecifies things quite a bit. So I made a couple references during the talk to something called JFIF, which is actually a companion, and there was like a segment in our file that was like a JFIF segment, and that's a companion standard to JPEG that basically says, okay, the JPEG standard is way too complex. This is like a subset that we're going to accept for like interoperable JPEGs. That like and then there's on top of that, there's another standard. I think, I don't know if it's called the XIF standard. I think it might be, but it's basically when people talk about XIF metadata, it's part of this standard, but it's like another standard on top of JFIF. At least that's my understanding, that like even more limits like what JPEGs are supposed to be. For my purposes, I just coded against the JFIF standard, but the JFIF standard guarantees things like having a certain number of components, or like using a specific YCRCB color space and things like that, so that different apps that write JPEGs can actually interpret the images that other apps are creating, because otherwise there's so much variance and it's not really easy to do. So yeah, there was a lot of like going in and then like cross-referencing like against like, oh yeah, and also on top of that, the JPEG standard is a paywalled standard that I didn't buy because it was pretty expensive. So I was working off of sort of secondhand resources relating to the standard, like Wikipedia articles or books and things like that. So that was fun. Well, I should probably cut this off so that the next person can go with their talk. But yeah, thanks everyone for listening, and feel free if you have any more questions to reach out on Discord. I'd be happy to answer them.
Awesome. Thank you, Thea.
Yeah, thank you so much.
Ready, Adam?
Yep, let me share my screen. And there we go. Everyone can see this.
Yep.
Cool. All right. Well, first, thanks for that talk. I have written many image decoders in my day and been very confused about the compression side. So certainly the animations were actually very helpful. When we should talk on Discord about the vicar image format, which is used in the space program that my wife and I wrote a decoder for a long time ago. It's much easier, much simpler. Turns out that 1970s spacecraft can only do a few things. But they can't write a good standard. So anyhow, my name is Adam Fletcher. I'm the CEO and co-founder at a company called Bit.io. One thing we're doing is building a Postgres compatible database. And inspired by Phil's post on the Data Station blog about Postgres wire compatibility testing, I wanted to tell the story about what it really, or what I think it kind of means to be Postgres compatible, kind of from a vendor perspective, like that's where we sit. But I'll talk about the various ways you could consider yourself Postgres compatible, give some anecdotes and examples, right? And talk and, directly kind of from our implementation. Many database vendors, including myself or my company, right, say they are Postgres compatible, right? But building a database is actually a pretty tricky thing, especially for startup. There's like not really an MVP that can be built quickly, since the minimum bar is like, don't lose all my data, don't corrupt my data, right? And also the comparables are stuff like Postgres and MySQL and commercial offerings, right? There's also a ton of libraries, clients, tutorials, Stack Overflow articles, and all the rest on like existing databases, and also for the language SQL that people use to query data, right? And so what most vendors do, most people building databases do, or other things that are supposed to be compatible with databases, they say like, great, I'm not going to reinvent the wheel here. I'm going to use the Postgres wire protocol, or maybe the MySQL wire protocol, right? And the advantages of doing that, obviously, you get access to all these clients that say they can talk to Postgres. We could, and we tell our users they can use their favorite Postgres tool to connect to us because that's so easy for them, right? Instantly, we get access to all of that. But what does it really mean to be Postgres compatible? I think Phil did a fantastic job of diving into this in his blog post. I'm going to talk about some of the other aspects of that. What I thought when we started Bit.io and what I thought about Postgres compatibility was literally like, oh, we'll just speak the wire protocol, right? And we'll parse Postgres grammar and that'll be it. We'll be Postgres compatible. Everyone will be happy, right? And I will, it's a simple matter of programming, right? And I was pretty optimistic about that, right? But we're going to talk about how wrong I was because, definitely that's not how this works. You don't, the stuff on the right is a great diagram, but don't worry about it. It's there for context to show you sort of that, some complications the protocol can have. But we'll start with the wire protocol, sort of the base of like, if you thought about Postgres support as broken up into like the OSI model of layers, like this is the bottom of it, right? Now, what we mean when we talk about a protocol is, it's like talking about HTTP, the protocol, not the web page you get back, but the HTTP get command or post or whatever, right? Like what's what we're talking about, the messages between the client and the server, right? To get done what the user's asking for. So we're gonna, so the Postgres protocol, kind of old. The version we all use today came out in 2003, but and you wouldn't really consider it that modern a protocol. It has sort of legacy things like when you want to use SSL with it, you actually have to inline in the protocol, say like, hey, let's turn on SSL. And then everyone turns on SSL and that great. But the measure of a protocol is not how modern programmers think about it. It is about adoption and it is about, and by that measure, by any means, the Postgres protocol is an enormous success, right? Everyone uses it, it's hugely adopted. The diagram on the right, made by Fantex, this, I'll send this link to the Discord in a moment or after this talk, is great, but the protocol itself is a message-oriented protocol where each message is prefixed usually by a ASCII uppercase letter, right? And then there's usually some follow-on to that. So a query message starts with a capital Q. Then there's the content length in bytes. Note that that says int 32. It does not specify whether that's an unsigned integer or not. Who knows? And then finally, the query itself, right? There actually is two different kinds of querying. When you're querying a Postgres database from the client to server, there's the simple protocol, and then there's the extended protocol. This, what you're seeing here, is the simple protocol. We'll talk about both in a little bit. Implementing a protocol is tricky, right? They are subtle and they are quick to anger. The specification for the authentication query flow is quoted here, right? And when we implemented this, we send some parameters and some key data, just like you see this thing says we should do. And for many clients that worked. We would just send them over whenever we got them back. We have a little proxy implementation, right? They would send them whenever we got key data, we'd send it over. Whenever we got parameter statuses, we'd send them over. Fantastic. That worked for a number of clients. Then it completely broke for a whole bunch of other clients, right? And a careful reading of this specification, you note it says finally there, which implies that the ordering is actually really, really strict. So we spent, I won't say it was a week or two, but we spent a while looking for this. And finally, we had to just go to the source and see, like, what is Postgres doing? What is the actual ordering here? Because the textual representation in the documentation says this. It's not very clear if they have to go in order. And some of our clients worked when some clients worked when these messages were out of order, but really it had to be in order. The clients that worked with it out of order still worked with it in order. And then we expanded, then we got all of the clients working. And that is like, there's very subtle things when you're dealing with a wired protocol like this. It has to be in order. I mean, I think, just like JPEG matters, right? Like those things have to come in order. And we, this is some of our test code pulled from our library. You can kind of see that this giant comment at the bottom is, I'm sure many of you, if you've written software, have a comment like this after you found a nasty bug and said, like, for future me, don't screw this up. Be very careful, right? This is just to note that these things happen in real life. Let's talk about transactions in the wire protocol, because I think they're kind of interesting. A transaction, or you could kind of think about it as a query, is maybe what people would normally think about it. There is the simple one we talked about earlier, where you just send over the literal query text, and then the server executes it and gives you back your results, which is good, but not very efficient. What you often want to do is use, and what clients are often doing behind your back, is using what's called the extended query cycle, or the extended query protocol. This is where Postgres will send over the parsed query, or the query to be parsed. The server parses it, caches it, stores it, knows about what parameters it needs to expect, and waits for the next set of messages with bind values to those parameters, and then finally it can execute it, right? And this lets the server cache that query. It lets it do better query planning. It lets it, modern libraries, very modern libraries, or clients to, not very modern, but just modern client libraries, all expect the extended query protocol to work. They all want to use it. If you're going to call yourself Postgres compatible, you have to support it. Now, there's lots of interesting things that can happen inside the extended query protocol about like transactions occurring in different orders and things like that. It's actually quite tricky to implement that state machine on the back end, but you have to support it, especially when you think about like binding values to SQL statements, right? Pretty obvious. There's also a number of other sub protocols inside the protocol, the wire protocol itself. There's a streaming replication protocol. There's a logical stream, there's copy operations that can be done. There's a message going back and forth for notices between the client and the server. And some of these you do want to implement, but you're not really I don't think you're actually required to implement them. I think you'd be fine calling yourself Postgres compatible if you didn't implement the streaming replication protocol. Clients are not trying to replicate, right? Now, you're building a product that's server to server, sure, that matters. But in this case, clients don't care, right? So what would I say is required for Postgres compatibility at the wire protocol level? right? And I know some of my coworkers on here who might tell me I'm wrong, but that's okay. I think you need to do authentication. You need simple and extended query. Copy operations are really nice, and a lot of programming language libraries use them to speed up data importing. And you need notices, but you don't need some of these other things like the replications or even direct function calls, which are a legacy deprecated protocol. Wire protocol is one thing. Sort of the next layer is both syntax and grammar. What I'd say here is that the actual SQL standard isn't really implemented by database vendors, which is to say it's an evolving standard. It has many years, like the C standard is not always implemented by every compiler. And there isn't like a reference implementation. It's not like the ANSI board implements a database that implements the SQL standard, right? And then what happens typically is that vendors implement a subset of the ANSI standard, all the stuff you'd kind of expect, and then they implement their syntax or vendor-specific syntax. And an example of that is like PL, PG-SQL, or T-SQL or stuff, but there's also like a whole bunch of other SQL language constructs that are vendor-specific, right? And I would say it's actually pretty easy to parse, to accept and parse the full range of PostgreSQL. The parser is open source, right? You can just go look at the Yak grammar for it. You can even use that grammar to generate new parsers, right? And I'm not going to go into too much detail here. The TLDR really is just go read Phil's post. I think he did a great job of covering the grammar and who can parse what, and so on and so forth. But and the other advice I give, if you're going to do this, there's no need to build this from scratch. Like there are a bunch of good open source libraries, including libpq and the built-in, obviously, the real Postgres parser, and that's what you should use. That said, it's not about parsing where the compatibility comes up. It's about feature support, right? Just because you have parsed and have like an AST for some SQL does not mean your server can execute it, right? You got to find out, you're going to claim Postgres compatibility. Well, do you support shobj description as a function call and give back an answer that clients expect? Do you support set config instead of using set? Do you support PG get serial sequence, right? Like these are all real customer asks for us early on in our implementation where we did not support necessarily these. One thing about our implementation is that we have a very interesting and strong permissioning model because we allow you to share and collaborate on data, kind of like you can do in GitHub or Figma or Google Docs. And so we actually have to override the implementation of some of these things. But I think that, you have to, if you're going to claim that you are Postgres compatible, you do have to implement a whole bunch of these features because clients are going to send them. These are clients just saying, oh, I'm talking to a database, I'm talking to a Postgres database, I'm happy, I'm going to send these off. Of course, they're going to be supported, right? Clients will use everything you provide to them. Right, and then another question really is, are you Postgres compatible with the community and the users? And I think this is kind of an interesting and overlooked thing where users will find an answer on Stack Overflow from 2005 that says that in order to like change the list, in order to get their PG SQL to run, they need to change the listening port of their server, right? That's what they'll find. That is wrong, but they're going to do it. They're going to try to do it, right? And then also another, you have other assumptions like Postgres is frequently run in an environment where people connect as the Postgres user and they have full control over the database. Now, that's not really a Postgres compatibility issue from the technical perspective, but what are the expectations you are setting with your user when you said you are Postgres compatible, right? Like, and kind of here, I list over on the right-hand side, that's code, these are like disallowed set commands for us. Like even if you tried to us as like what you would consider the, sort of root user, the Postgres user, you can't run these set commands. Like we don't want you changing the listening port of our service, right? Like, I mean, it's not really how it works, but you understand. So what would I say is required kind of in the feature compatibility for most clients, right? I'd say that there's a lot of functions that start with PG underscore. Almost all of those you're going to need to support in some way or find an answer for, right? You don't have to necessarily do what it says on the tin, but you should reply back with something. Clients often want to know definitions of like tables, indexes, views, et cetera. Like they want resource definitions, especially like you can imagine you're a SQL client, you're going to go get the views that are implemented and say like, hey, what is the definition of this? Because in case someone wants to change it on the client side and save it. You need to support session-based setting. You need to support things like setting the locale for people. Those are just session-based set commands. So like set commands can be applied to the server. They can apply to just the session. You need to support all the data types, of course, the Postgres data types, which you may think are just SQL data types, but they are not. They are a variety of data types. If you've used Django, for instance, the JSON data type was only Postgres supported until the latest version of Django, right? Because Postgres has the JSON data type, but MySQL didn't, or they just didn't implement it if MySQL does. You have all of these kind of interesting things. Finally, you really do need to implement good messaging back to the client about what's happening. We found in our implementations, right, for what we do, supporting PL/PG SQL was not a requirement. Most people don't use it, and for people who do use it, that's a different story, but we haven't really not run into that many people that use it. Of course, we've turned off replication stuff and some of the set commands. But really, like, Postgres is super featureful, and unless you are Postgres, you're not going to actually fully support Postgres. You'll never be, I think, feature compatible with Postgres unless you really are just Postgres. Like, that's fine, but that's just kind of how it is. And as I kind of said, there is this bit of a sort of my crappy analogy to the OSI model, right? There are these layers that build upon one another. There's the wire protocol, there's the grammar and syntax, there's the features, and then finally the community and user expectations, right? And I think that to say you're Postgres compatible, you want to kind of hit some of these bullet points, and these are the ones I kind of imagine you being able, you kind of required if you're going to talk about it like this. The one thing I will say, the one takeaway from this talk that's important is client support defines Postgres compatibility. It's you build your server to work with the clients you have, the users you have, and what clients they use, rather. Right? That's what defines the Postgres compatibility. There's a huge ecosystem of clients, and there's a bunch that your users are going to use, a bunch they won't use. Kind of need to know what they're doing. There's no way to do that, but dive in and see what happens when people use it, right? So take this away. This is the big action. This is the big thing for you to know. Client support defines Postgres compatibility. Nothing else does. Doesn't matter what anyone says about their wire protocol, whatever. Got to support the clients. Cool. And that's it. That's my talk. Of course, you should go sign up for bit.io. Got to say it. Also, we're hiring. And also, did I mention we are Postgres compatible, for whatever that means? Go read Phil's post. It's great. Fantax also has a great deep dive into the Postgres protocol flows, the state machine you have to implement, and all of the usual stuff. If you have any questions for me, I'm on the Discord. Happy to answer them right now. We actually also have some other experts on here. You can send me questions, adam@bit.io. But that's about it. Happy to turn it over for questions.
I'll get us started. Oh, go ahead, Caleb.
So you had a slide where what's required for wire compatibility and what's not, and that you have some disagreements possibly with the people with your team. What are those differences? Do I think there's certain things that aren't required that you think are? What just like expand on that bit?
Yeah, that's a great question. There are actually people from my team on this call that maybe could call me out. I think we would get into conversations like, is copy really required? For instance, I think it is. Maybe some people say, well, you don't really need it. Like, how often is anyone really using it, right? Probably there's some while we say direct function calls aren't necessary, it is a thing that old Postgres clients might do. People might have code that does it, right? And that's kind of why I say it's like defined by the actual clients that use us, right? And so it's interestingly kind of a product decision, not a technical decision for some of these. And that's really true, I think, in a lot of ways, for anyone, right? I mean, I think about like Phil building DataStation, like for Postgres compatibility, he doesn't care about replication protocols, right? He's never going to build that. I mean, maybe he will just because it comes in the library he's using, but do you know what I mean? Like that's not important. So it's very much a product decision.
So yesterday, I think there was a company on the front of Hacker News that was doing like access all your databases through Postgres, and the way that they implemented that was a foreign data wrapper, which is also pretty common. So I'm curious, when you were building this, what was your thought process behind implementing it as a foreign data wrapper, where you would get all this stuff for free, or I'm just curious about the trade-offs.
Yeah, I think there's a lot of trade-offs there. I mean, this one is how you implement foreign data wrappers, and like we hold all the data and we are the single source of truth, and the nature of the permissioning model we do and the way we store the data doesn't really let us do this with foreign data wrappers. For us, I think foreign data wrappers are a great way to do many things. And I do think though that there's like tricky bits about foreign data wrappers and other things is, you know, which like if you're querying using Postgres syntax through to Snowflake, like if you have any Snowflake specific needs, like you get the sort of least common denominator of all the features, right, between the things you're working with, and that's just something you have to be aware of. It's fine, but there's just stuff you have to be aware of, and also type mapping, I assume. Now, I don't know too much about the foreign data wrapper system, so maybe that's handled in there. I don't want to claim it is or isn't, but there's other projects out there that do basically proxying and things like that may handle some of that.
But whether or not you implemented the wire protocol versus implemented through using it for data wrapper, like that's not whether or not you're supporting Snowflake syntax. In both cases.
Oh, sorry. Yeah, sure. In the wire protocol case, you're fine. Yeah. Sorry, I cut you off. Go on.
Yeah, never mind. I'll ask you offline.
Okay, sorry.
It seems like there's a lot of complexity and a lot more complexity than I would have expected in the Postgres wire protocol. I'm curious, what would you say the like percent split of like time that your company has spent on Postgres compatibility versus like time like developing the storage engine or, you know, other features that are like not related to Postgres?
Oh, that's a good question. I think we really have consistently had probably 1.5 to 2 full-time engineers working on various aspects of Postgres compatibility.
Wow.
A lot. So, but yeah, because it can take because we want almost all of this stuff, right? Like we have a much broader set of needs than just wire protocol compatibility. Like we're trying to do a lot more of these things. I do think that that comes and goes. Like that includes, we're only about 2 years old, and a lot of that was initial implementation of it. And so I bet that should decline and fall off as we mature, because it and as we get better at it.
Do you think it'd be possible for Postgres to like librarify more of the code, or basically expose more of Postgres so it's easier to integrate this stuff without having to write it from scratch yourself? Or do you think it's like very tightly coupled to like Postgres's storage engine or your storage engine in a way that would make that difficult to share?
So I guess I didn't really talk about like semantic versus syntactic meaning. I think that is the tougher part, right? Like, does it do kind of what do you get the same effect when you run something on my storage engine versus your storage engine versus Postgres' storage engine? The Postgres code base is very well broken up, and it does have some libraries, and they do a very, very nice job. The code is extremely readable for being a 20-year-old C code base, right? Like, it's actually incredibly readable. They've done a fantastic job. So I think that, and then I also have an extensions engine, which I've not personally worked with, but I know some other folks have. I think there could always be more places for the extension hooks. Then there's probably a lot more. I don't know as much about foreign data wrappers, but there's probably a lot more that could be done there. There's other ways to do this. I think that, or do things with Postgres. It's pretty extensible. People have been working on it for a while. I think the issue is not necessarily the server side. I think it's that you have to deal with an installed base of clients that have expectations, and that's the question, right? Do you handle all the things they do? Do you handle all the expectations they set more than I think necessarily on the back end side? If that makes sense, right?
Yeah, like even if like you had a Postgres library that magically handled all the wire protocol for you, that's still not going to help you decide like how to handle when someone does like set port 8888.
Yeah, right, exactly. Like we have to deal with that. Yeah. One thing, we have a very interesting permissioning model. Like we move the permissioning and stuff like kind of outside of any Postgres. Like we do have our own control plane for handling a bunch of things like that, and that has been a really interesting implementation challenge. And you could imagine a world in which way Postgres does that is like not just pluggable auth, but pluggable permissioning of some kind, right? And it can just message us stuff, or we could sit in the flow or write an extension to do it. And that's not that easy to do on the server. We looked into that and we decided, well, that involves like forking Postgres and writing a whole bunch of C code and doing all this. And we're like, well, that's not really worth it for what we're doing, right? And doesn't actually answer our problem in any way, shape, or form. Like, would I prefer Postgres to like speak protocol buffers and like do all these things? Yeah, of course. But like, there's a cost to that, and it wouldn't necessarily be accepted if you contribute it back to core Postgres.
Yeah, it'd be like a huge breaking change. Well,
Yeah, right. And totally understand where they're coming from. And this is not at all a criticism of that. I think I would say the same thing if I were in their seat. Happy to answer any more questions anyone has.
So since there are so many databases, what made you do your own?
The sharing and collaboration portion of working with data. So everywhere I've ever worked, I've ended up having to build some sort of system that allows people to share and collaborate on all of the various local databases they have or data they have. Me and my co-founder have done this a number of times, and it's always a huge pain, right? It's always required like, senior engineers building a bunch of ETL stuff or building, knowing a lot about the technology or writing code, writing actually systems like we've built here. But instead, like on bits.io, it's like single click sharing, single click permissioning. You can just go to our site, like drag a file, get a database, and then if I want to share it with you, I can just share it. If your username was Jorg, I would just share it with you by username, like you do on GitHub or like you do on Google Docs. And you don't have to do any firewall, you don't have to do IAM, you don't have to do any RBAC, you don't have to do any of that stuff, right? And you can query my data if I've shared it with you and your data in a single SQL statement, right? If you've shared, if the permissioning. So you can also make your data public or private. So it adds a whole dimensionality to the non-data side of it, the collaboration, the sharing, the social side of it, that I think is very hard. We see most people are doing this with either a whole lot of data engineering and transformation, or they're doing it with exports, or they're doing it, in these terrible, terrible ways. Sorry, yeah. Any other questions? Cool. I'll be on the Discord. Happy to share. I know we can get a bunch of other people on the Discord, maybe from bits.io, or just come try us out. And thank you very much.
Cool. Thanks, everyone, for coming. Thank you so much for Theia and Adam for sharing tonight. I learned way more about JPEG than I ever want to. Yeah, so this talk will be available on YouTube. I'll ask Theia and Adam to post their presentations in the Discord channel, HackerNice Discord channel. Next week, we have Simon Erickson, author of the Napkin Math blog. I don't know if you've heard of that, but it's an amazing blog. If you Google Napkin Math, you'll see it. He is coming to talk about bandwidth measurement, like Napkin Math bandwidth measurement, I think. Also that week, we have the author of RQLite, which is distributed SQLite. He's a engineering manager at Google. So the two of them are coming to speak next week. He's going to talk about RQLite. We've got another spot open there. It might be filled by Josh, who might be talking about Bazel, but I'm always looking for speakers. You don't have to be a professional about what you're speaking about. You can do what I did and just talk about something random that you learned, do what Theia did, talk about something random they learned. Yeah, anytime anyone wants to share, just let me know. And I'm going to stop recording now and give, last week, we just, people who felt like hanging around and talking are welcome to hang around and talk, and we'll keep the Zoom on for another like 10 or so minutes for that. So thanks, everyone, and I'm going to stop recording now.